we continue to study linear algebra. Okay. So for today's is the third class. Okay. And I hope all of you enjoys this course. Okay. Actually, this course is not difficult, but you need to take more time to review the content. Okay. To do the homework, also for exercise. Okay, you must discuss with the TAs if you don't understand some content or some exercise, and then he will give you some suggestions or possible solutions. Okay, so for now we go to for lecture 1 part 2. Okay, and we need 1.5 class to finish lecture 1 part 2. Okay, and of course TA will make a recording of the lecture today. Okay, and then maybe he will upload the recordings tonight or tomorrow. Okay, it depends on his free times. Okay. Okay, so for now I will share my screen to all of you. And if you have any question or any discussion, okay, please interrupt me and ask me, or you can type some questions into this message chat, and then I can know your questions. Okay. Okay. So for now we go to lecture 1 part 2. Okay. We discuss about systems of linear equations and matrices. Okay. So this lecture is very significant for the course of linear algebra, because we will study what the linear equation is and what's the system of linear equation. Okay, also matrices. Okay. So for the contents of lecture 1, the part 2 is here. Okay, we discuss about the introduction to the system of linear equation. Okay, so first of all, you should understand what's a linear equation, right? Yeah, what is a linear equation? Okay, after that we combine many linear equations. Okay, we can get the system. Yeah. We study the Gaussian elimination. Okay, so to solve the system of linear equation, okay, we need to apply Gaussian elimination method. Okay, and then we discuss some application of a linear system. Okay, maybe we apply the linear system into electric circuit theory. Okay. So now we go to the first session 1. Okay, so what's a linear equation? Okay, so here we have the definition of a linear equation. Okay, yeah. A linear equation in the n variable x1, x2, blah blah to xn to be one that can be expressed in the form here. Okay, so this one is linear equation. Remember that we have italic, right? Italic. For example, we have x1, x2, x3, blah blah blah. They are italic, so they are all variable, right? Variable. Remember that if we have capital, for example, capital I, okay, this is constant. This is the constant value. So if we have italic letter, that means they are a variable. Okay, so now we have a1 times x1 plus a2 times x2 plus blah 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 plus an times xn equal b. Okay, so a1, a2, blah blah, an are constant. Okay, and x1, x2, blah blah to xn are variable. B is also constant. So this one is linear equation. You can see we have many different variables, but they are in the power of 1, right? X1 to the power of 1, you get x1, right? Yeah. So all variable, okay, have a power of 1, power of 1. Yeah. So this is the linear equation definition. Yeah. Okay. Again, this is the general formulas of linear equation with n variable. N variable. Okay. X1, x2, blah, 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 to xn. And we have n coefficients. Vietnamese meaning hệ số. Okay, so we have n coefficient a1 blah 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 to an. Okay, so you can guess the linear equation, right? A1 x1 plus a2 x2 plus blah 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 plus an xn equal b. Okay, so we have two cases of b. B is 0 or b is different from 0. Okay, right? We have two cases of b. B is 0 or B is different from 0. So if B is 0, okay, so if B is 0, you can get A1 x1 plus A2 x2 plus blah 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 plus AN xn is 0. So this equation, okay, so this equation is called by homogeneous linear equation. Vietnamese meaning phương trình tuyến tính đồng nhất. Okay, so yeah, remember that if b is 0, okay, you can get a homogeneous linear equation. So if b is different from 0, you get the general format here. Okay, yeah. Okay, so for example, if we have two variable, we have x1 and x2. So we have linear equation is a1 x1 plus a2 x2, okay, equal to b, like this. Okay, so if we have three variable, we have a1 x1 plus a2 x2 plus a3 x3, okay, equal to b. Okay, yeah, so it depends on how many variables we have, how many coefficients we have. Remember that the number of variables will be equal to the number of coefficients. Okay, so look, we have three variables, so we have three coefficients. Okay, next. Okay, so anyway, here we have the definition of linear equation in n variable. Okay, yeah, we have n variable x1 x2 x3 blah blah xn. Hey, the form a1 times x1 plus a2 times x2 blah blah blah, okay, equal to b. And we have coefficient we discussed before, right? A1 a2 a3 blah blah an are real number, remember, real number, coefficient, a real number. And the constant term, okay, the constant term b is also a real number. Okay, then they also give us the concept of the leading coefficient and the leading variable. What does this mean, the leading coefficient and the leading variable? Look, so if we consider the linear equation, this is the first term, right? This is the first term. This is the first term. We have a1 x1. Okay, because is appear first. Okay, so A1 is leading coefficient and X1 mean leading variable. Okay, variable. Yeah, remember that. Okay, A1 is the leading coefficient and X1 is the leading variable. Okay, for example, for example, uh, we have the linear equation like this. How many variables we have? Four variables, right? X1, X2, X3, X4. Okay, and we have X1. X1 is the leading variable, right? Variable. Variable. And A1 is what? Okay, A1 is 1. This is leading coefficient, right? X1 or 1 times X1. So A1 is 1. Is a leading coefficient. And X1 is a leading variable. Okay. So this one is also a linear equation. Okay, so we don't want to use x1 and x2. They would like to use x and y. That's okay. Okay, they are also variables. Okay, so we have x plus 3y is 7. This is linear equation. Here, they use x, y, z. Okay, they don't want to use x1. They don't want to use x1, x2, and x3. That's okay. They can use x, y, z. Okay, so x is the leading variable and 1 over 2e the leading coefficient. Okay, similarly, here we have x1 plus x2 blah blah plus xn is 1. So x1 is leading variable and 1 is leading coefficient. Okay, now we consider this one. The following are not linear equation. For example, this one is not linear equation. Why? Because we have the power of 2. Okay, and if we come back to the definition of linear equation, okay, all variable must have a power of 1, but here we have the power of 2, so this one is not linear equation, right? Yeah, and this one is also not linear equation. Why? Because we have the product. Okay, so if we come back to the definition, we don't have any product of variable in the linear equation. Okay, so remember that a linear equation doesn't involve any product or root of variable. For example, this one we have the square root of variable, so this one is also not linear equation. Okay, how about this one? This one is also no linear equation. Why? Because we have psi x. Okay, so look, on variables occurs only to be the first power, and don't appear. For example, a is the argument of trigonometric, okay, logarithmic, okay, and exponential function. Okay, okay, so this one like trigonometric function because we have psi x, okay, psi x, okay, cosine x, okay, tan x, blah blah blah. This is these are they are trigonometric function, okay, trigonometric function. Okay, so if we have trigonometric function, we have logarithmic, okay, and exponential function. Of course, they will not be linear equation. Okay. Yeah. So now, up to now, try to clearly understand the definition of a linear equation. Okay. So and then we have some we have some not linear non-linear equation like this. Okay. So this one we say non-linear equation. Now this one we say linear equation. Okay. Yeah. Now for this course focus on linear, right? So we forget this one. Okay, we just focus on a linear equation. But in the future, we will study another course, non-linear programming. Okay, non-linear control, non-linear engineering. Okay, here I mean if you study master degree, okay, you will study the course of the non-linear uh, programming, non-linear engineering. Now we are undergraduate students, so we just focus on linear algebra, linear equation, linear engineering in the first year. Okay. So example. So now you can uh, check whether these equations are linear or non-linear. So this one we have 3x plus 2y is 7. Yes, this is linear equation. Okay, x, y, and z. Okay, by a 3 by 14. So this is constant. So this is linear equation. Okay, psi by, you know. Of course, we have psi, but this is psi by is a constant, right? By is a constant. So we have psi by is constant. Okay, so psi by is what? Is 0. Okay, so that means here you can get 0 x1 minus 4x2 e to the power of 2. Is constant. Okay, is constant. So this one is constant. So this is a linear equation. Okay, and here they are non-linear equation. Why? Because here we have the product of variable, right? X times y. This is exponential function. Okay, e to the power of x is exponential function. Okay, this is the exponential function with x variable. And now, okay, we have psi x1. Okay, very different with this one, you know. For this one, we have psi by, but this one we have psi x1. Okay, so of course, there is a not linear equation. Okay, any question, please? Okay, let me check if you have any questions or not so far. Okay, so no questions. Yeah, good. Come back. Okay, so continue. Now we talk about of linear of sorry, system of linear equation. Okay, so if we combine many linear equation, it will become a system, right? So here, how many linear equation we have? 1, 2, blah blah, m. Okay, we have m equation. Yeah, we have m equation. How many variables? Every equation, right? Every linear equation we have x1, x2, blah 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 to xn. So every equation we have n variable. So we have n variable per equation, right? Yes. Okay. So that means we say a system, right? A system of m and n. What does this mean m? What does this mean m? We have n, so m that means m equation. Okay, and n variable per equation, right? Yeah. For example, here, this is the linear system, right? This is a linear system. Sometimes we say linear system. Sometimes we say a system of linear equation, the same. So here we have two equation and two variable, right? Two equation, two variable. Here we have the linear system, right? We have two equation and three variable, two equation and three variable. And this one we have m equation and n variable. Okay. Yeah. So now you understand what is the linear equation. What is the linear system? Of course, the linear system is the combination of many linear equations. Okay. Yeah. Now we look at the sentence. Okay. Here we have the double subscription of coefficient Aij. Look here. Yeah. Okay. For the coefficient, okay, for coefficient we have two subscript. Okay, this is the first one, the second one. So the first subscript indicate the equation in which the coefficient occurs, and the second indicate which unknown it multiplies. Okay, for example, we have a12. So a12 is in the first equation and multiply x2. Okay, yeah. So for example, we have a13. So 1 mean the first equation, right? And 3 mean multiply, okay, multiply x1, x3, okay? Yeah. Multiply x3, okay? So if we have a2, 4, if we have the coefficient a2, 4, that means the second equation, right? The second equation. And multiply with x4 of what? Of second equation. Of second equation. Here. a24 somewhere here. Yeah. a13, that means the first equation, and multiply x3 of the first equation. Okay. Yeah. Yes. Okay. So now you need to remember the general representation of linear systems. Okay, we have a11 x1 plus a12 x2 plus blah 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 plus a1n xn equal to b1. Okay, the first equation, so we have b1 and blah blah blah. We have m equation, right? M equation and n variable. So m equation, so we have bm, right? So we have am1 x1 plus am2 x2 plus blah 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 plus amn xn equal to bn. Here we say linear system. Here we say linear system with m equation and n variable here. Okay, 1, 2, blah blah, m equation, right? And n variable. Okay. Yeah. So now we discuss about the solution of linear system in n unknowns x1, x2, blah 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 to xn. Okay. So how can you get the solution of this linear system? Okay. So that means we have solution x. This is the vector, solution x. So solution x is to contain x1, x2, blah 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 to xn. For example, if we have 2x1 plus x2 e3, okay, and x1 plus x2 e2, something like that. Okay, so if of course this is the linear system. Okay, so if you answer this linear system, you can guess x1 is 1 and x2 is 1. Do you agree with me? Yeah. So that means you get the solution. Okay, the solution contains x1 and x2. Okay, so you can get what? You can get 1, 1. Okay, 1, 1. Or you can say we have the vector, the solution vector x is 1, 1. That means x1 and x2. Okay, yeah, yeah. So if we have n variable, if we have n variables, so you get the solution is what? x1, x2, blah, 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 2xn. Okay. Yeah, this is the solution of, okay, this is, yeah, this is the solution of this linear system. Okay. Any questions? Maybe I go fast or I need to go slowly. Okay, so if you need you need me to teach slowly, okay, I will follow. Or if you feel boring, you would like uh, go quickly, okay, I will follow all of you. Okay, it depends on your requirement. Okay. Any questions so far? Sorry. Okay. So if no questions, continue. Yeah. Sorry. 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 So we have example. We talk about parametric representation of a solution set. Okay, parametric. For example, why we say is a parametric representation of a solution? Look. This is a linear equation. Okay, how many equation? One equation. How many variable? 1, 2, 3. Okay, so coming back to the high school, if we have one equation and then we have 3 variable, you cannot determine x, y, z. Okay, yeah, we cannot determine x, y, z. Why? Because we have 3 variable, but we only have one equation. Okay, now we think further. Okay, so now I try to random select the value of y and z. Okay, so I don't know how to calculate x, I don't know how to calculate y, I don't know how to determine z, but if I assume y is and z e t, okay, of course s and t belong to real number set. Okay, this is real number set. Okay, I can assume any arbitrary values of s and t. Okay, so now you get x. Okay, so we have 3xe, 3 minus 2y plus x. That means we get x is what? E1, right? Minus 2 over 3y plus 1 over 3z. Okay, and x is 1. Okay, And y is what? Y is what? Y is s, so you get minus 2 over 3 s. And z is what? Z is t, so you get plus 1 over 3 t. Okay, so now you can get the general solution, right? We can get the general solution. Z is t, y is s, and x is 1 minus blah blah blah. Okay, yeah. So now I can indicate the solution. Where the solution and the solution. Maybe I use the solution is maybe I use the solution is just vector x. Okay, so the solution has three variable, right? X, y, and z. Okay, so now x is what? X is 1 minus 2 over 3 s plus 1 over 3 t. Okay, and y is what? Y is s and z is t. Okay, yeah. So this is the general. This is the general solution, right? This is the general solution of this linear equation. So if I say y is 0, I assume, I assume y is 0 and z is 0. Yeah. If I assume y is 0 and z is 0, so y is 0 and 0, that means s is 0, right? And t is 0, right? So you get x is 1. Okay, just one particular solution. Another one, if I assume this y is 1 and z is 2, so y is 1, that means s is 1, and z is 2, that means t is 2. Okay, so you get 1 minus 2 over 3 plus 2 over 3, so you also get x is 1. Okay, so we have many solutions. Okay, many solutions, because we don't know the certain values of y and z. Okay, we just say y is a random value of s and z is the random values of t, and s and t belong to R. Okay, yeah. So yeah, so we can get the general solution of this linear equation with here. Okay, any questions? Okay, no questions? Okay, continue. Okay, so yeah, now we use the graphical representation, okay, to determine the solution of linear systems. Okay, here we have the linear system with two linear equation, right? Yeah, we have a1x plus b1y equal to c1 and a2x plus b2y equal to c2. Okay, we assume here is the first equation, right? We say f1, and here I say f2. Okay, so this is the f1, right? Then this one is f2. So they are in parallel, so we have no solution. Now this is f1 and this is f2. Yeah, they have one common point, okay, or one interconnection, right? Or common point. Okay, so that means they have one solution. Now we have f1 and f2. They are coincide. Okay, they are coincide. So that means we have many points. Okay, many points mean many solutions. So we say this linear system has okay, infinitely many solutions because they are coincided. Okay, coincide. Any questions? So, in summary, you can use the graphical representation, okay, to determine whether these linear systems has the solution or not. Okay, so we have three possible, solution, right? Three possible solution. The first one, no solution. The second one, only one solution, right? Only one solution. And the third one, we have many solutions. Okay, so every linear system, okay, they have three possible solutions: no solution, one solution, and many solutions. Okay, yeah. Example here we have x plus y is 3, okay, and x minus y is minus 1. Okay, so they have only one common point. Okay, that means x is 1 and y is 2, right? So if x is 1, y is 2, you get 3. X is 1, y is 2, you get 1 minus 2, you get minus 1. Yeah, correct. So we conclude that this linear system has only one solution, right? Only one solution. Now we have x plus y is 3 and 2x plus 2y is 6. Okay, so they are coincided. Okay, they are coincided. So we conclude that we have many solutions. Now we have xy, x plus y is 3, and x plus y is 1. This one is x plus y is 3. This one is x plus y is 1. Okay, they are in parallel. Okay, so we conclude that no solution. Okay, no solution. Yeah, yeah. So anyway, we can use the graphical representation, okay, to determine whether the linear system has the solution or not. Okay, yeah. So for this is the summary. No. For a system of linear equations, okay, precisely one of statements below is 2. Okay, the system has exactly one solution. We say consistent. The system has infinitely many solutions, and the system has no solution. Okay, so observe this one. You can see if they have one solution or many solutions, we say the linear system, okay, is consistent. You know, consistent. Or we can say if the linear system has at least one solution, so the linear system is consistent. Otherwise, if no solution, that means the linear system is inconsistent. Okay, inconsistent. Yeah, inconsistent. So, in other words, you can say if the linear system has at least one solution, the system is consistent. Otherwise, the system is inconsistent. Okay, please try to remember the concept. Okay, consistent and inconsistent, because next lectures, okay, I will ask you whether the system is consistent or not. Okay, and you need to demonstrate. How to demonstrate? If the linear system has at least one solution, the system is consistent. Otherwise, yeah, the system is not or inconsistent. Okay. Yeah. Okay. So yeah. In general, we say that a linear system is consistent if it has at least one solution, and inconsistent if it has no solution. Okay. Yeah. So there are only three possibilities: no solution, one solution, and infinitely many solutions. Yeah, we discussed before. Okay, we discussed before. Okay, yeah, yeah. Okay, look, every system of linear equation has 0, 1, or infinitely many solutions. Okay, so there are no other possibilities. Okay, next. Now from yeah, we consider the surface. This is the surface, right? Okay, this is surface. So to get the surface, okay, you need actually it's a two dimension, right? Okay. So now we have the surface, not the line, not line. This is surface. So here we have three surface, or we say three planes are parallel, so no solution. Okay. Two parallel planes, okay, but and no common intersections. Okay, of course, for this line, okay, for the surface the one and surface two, and this line for circuit 1 and circuit 3, but we don't have any common 1, 2, and 3 together. No, so no solution. Similarly here, no solution, no solution. Now look, this is surface 1, surface 2, and surface 3. Blend 1, blend 2, blend 3. Okay, so they are the common. Okay, they are the common line here, right? So we have one solution. Yeah, one solution here. Sorry, one solution here. Here. Okay, now look. Okay, this is number 1, number 2, number 3. We have three blends, and they have a common line. They have a common line here. So we have many solutions. Yeah, we have many solutions. Now, they are all coincided. Okay, so we also have many solutions. Okay, here, the same, Yeah, this is the common. So we have many solutions. Okay. Maybe here is 1, 2, and here 3. This one, the 1, 2, 3, they are all coincided. Okay. Only coincided. So we have many solutions, one solution. And here, all of them here are no solution. Okay. Yeah. Solving the system of linear equation. So if we have the questions, if we have a linear system like this, okay, we have three equations, right? Yeah, we have three equation and three variable, right? 1, 2, 3. So we have three equation and three variable. Okay, what are variable? X, Y, Z. Okay, we have X, Y, Z variable. Yes, we have three equations. Okay, so we try to modify this linear system to become this one. Okay, so for this one, the first equation, how many variable? 1, 2, 3. Okay, the second equation, how many variable? 2 variables. And for the last equation, how many variable? 1 variables. Okay, so that means we reduce, right? Right, we reduce the number of variable equation by equation. The first equation 3 variable, the second equation 2, and the last equation 1. Okay, so when we perform these systems, we say row echelon form. Okay, so this system is in row echelon form. Row echelon form mean step stair, sorry, stair up, step up stair or stair step. Okay, I mean if you stay here and you look back, okay, we can see the last equation 1 variable, previous equations 2 variable, and the first one 3 variable. So that is the reason we say back substitution. Because you get ZE2. Okay, so and then you use the equation 2, you can get y is what? Y is minus 1, right? And then when we have z and y, you replace into the first equation, you can get x. So xe 9 minus 6, okay, minus 2, you can get 1. Okay, so we have the solution xe, x, y, z, and this a, right? 1 minus 1, right? Right? Yeah. 1 minus 1 and 2. Okay. I'm right. If y is minus 1, and here you get 6, you get 5, right? And xe is 1, y is minus 1, you get plus 2, and z, you get plus 6. Okay, you get 9. Okay, correct. Okay, so the method, you get x, y, z here. The method you get x, y, z here is back substitution. Because you stay here. Okay, you stay at the last equation. Okay, you stay at the last equation, and then you look back to the first equation. We say back substitution. Okay, and the performance to get this linear system, we say row echelon form. Okay, any questions? Okay, so I will go back to check whether we have some question or not. Okay. Yes, we have the questions. We have the question why we should know the leading variable and coefficients. Okay, this is a good questions. Okay, I will answer to you later. Okay, yeah, we have some slides in relation to leading variable and leading coefficient. Okay, yeah. Why should we write the vectors on the top of x? Okay, yeah, I will answer these questions. I use the vectors because here we have 3 dimension, right? 3 dimension. Okay, three dimension. So if we have many variables, many dimensions, normally we use vector to imply we have more dimension. Okay, for example, we cannot say x because actually this one is bond face. Bond face mean a vector. Okay, so that is the reason I use up arrow to let you know this is the vector. And if we have a vector like this, okay, so if we have x, y, right, any vectors, for example here vector a, okay, we have vector ax, right, and we have vector ay. So how many dimensions? Two dimensions. Okay, so if I use vector x here, that means we consider two dimension x and y. Or if we have x, y, and z, okay, so we should use vectors. We have x, y, z. Okay, so if you don't want to use x, y, z, you can use x1, x2, x3. Okay, that is the reason I say the solution is the vector, or we say the solution vector. Yeah, and we also mentioned before, right? If we have n variables, we have n dimension. Okay, is it clear for you? Okay, I hope you got it. And then I will come back to these questions before later. Okay, why we should know the leading variable and coefficient. Okay, this is good questions. Later on, I will explain to you. Okay, yeah. So next, yeah. Okay, now look. Row echelon form of the linear system, or we say our stair step, right? Stair step patterns with the leading coefficient. Okay, so here also, the answer to the question why we need to know a leading coefficient or a leading variable. Now we come back to this one. Okay, maybe I will copy it, then I move to here. Okay, yes, okay. Yeah, okay, yeah. So now if we consider this one, okay, if we consider it, then we have x minus 2y plus 3z is 9, and minus x plus 3y is minus 4, and 2x minus 5y plus 5z is 17. So look, this one is, so if we consider the first equation, this is leading variable, this one. Okay, so we have here the leading what is x and coefficient is 1. Here the leading variable is x and coefficient is minus 1. Here the leading is x and coefficient is 2. Okay, we have the same leading variables, but now if you consider x minus 2y plus 3z is 9, and y plus 3z is 5, and z is 2. Okay, now this is the leading variable. This one is leading variables, this one is z. Okay, why? Because for the second equation we don't have x, so y is the leading variable, and here is z the leading variable. So now we have leading variable is x, leading coefficient is 1, this one is y and coefficient is 1, and this one is z and coefficient is 1. Okay, yeah. Yeah. So we have different leading variables and leading coefficients. Okay, from case A and case B. Okay. Yeah. For case B, you know, we have different leading variables. Of course, we have the same leading coefficients for all the equation, but we have different leading variables. Okay. Then if I use just coefficient, okay, if I use coefficient, okay, the first equation I get 1, minus 2, and 3. The second equation I get minus 1, 3, and 0. And the last equation we have 2, minus 5, and 5. Okay. Yeah. Yeah. This one we say is coefficient matrix. Okay. We just pick up coefficient. Okay. Here 1, minus 2, 3, minus 1, 3, 0, 2, minus 5, minus 5. And here, okay, you can get coefficient is what? 1, minus 2, 3. Here is 0, 1, 3. Here is 0, here is 0, and here is 1. Okay, so now you can see here this is the leading variables of x, leading variables of y, leading variable of z. Okay, because this one is 0, right? It is 0, 0, 0. Okay, so the leading entries for every equation here 1, 1, 1. Okay, yeah, leading variable x, y, z. Okay, and the leading coefficient are also the same 1. Okay, yeah, yeah. So if we know leading variables, leading coefficient, okay, you can compare this one and this one. Okay, yeah, just one of the answers. Later on, so we have more answers, more reasonable answers about that questions. Okay, okay, so for come back other questions so far. Okay, so next. Now, okay, just let you get more understand about back substitution. Okay, so for now, this one like row echelon form, right? That means step. Okay, the first equation we have two variable, and the next equation we have one variable. Okay, so this one like a step. So if we have y is minus 2, so x is 1. Okay, so we apply back substitution methods. Okay, back substitution methods. And then you can get the solution x a is what? A two dimension, right? Yeah, we have x and y, then you get 1 and minus 2. Okay, continue. So just more information. So the term back substitution implies that you work backward. Okay, backward. Okay, you calculate y, and when you get y, you calculate x. Okay, we say backward or back substitution. Okay, next. Then okay, so yeah, we also consider this one, right? This one is row echelon form. But later on, we have more information about row echelon form. Now we just focus on this one. We have z, one variable, there are two variable, three variable. Okay, so the number of variable reduce gradually from the first equation to the last equation. Okay, you can get z is 2, and then y is minus 1, and x is 1. Okay, yeah. So for we have this we have the observation, right? We have the observation. So if we have row echelon form, we can determine the variables very quickly, right? Very quickly. Because if here, this is row echelon form, and then you can apply partial substitution, you can get x, y, z very quickly. If z is 2, you replace into this equation, you get y. When you get y, z, you replace into here, you can get x. Okay, so you can get the solution very quickly. Okay, so that is the reason why we use row echelon form. Okay. So for now, the question, we have the question. How can we get the questions? How can we get the row echelon form? Echelon form, right? Of course, we know if we have the row echelon form, if we have the row echelon form, okay, you can guess x, y, z very quickly. But the question is, how can we get the row echelon form? Okay, how can we get the row echelon form? So if we have 3 equation and 3 variable, maybe you get row echelon form very quickly. But if we have a11 x1, right? Yeah. If we have a11 x1 plus a12 x2 plus blah 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 plus a1 n xn equal to b1 and blah 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 am1 x1 plus am2 x2 blah 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 plus amn xn equal to bm. So if we have the linear system like this, how can you get row echelon form? Okay, so to answer these questions, okay, we need to consider some rules. We need to consider some theory to help us answer the question, how can we get the row echelon form? Because if you get the row echelon form, you can get the solution of linear system very quickly, right? Right? So to answer these questions, you need to understand this one. Okay, so to get okay, what is our purpose? Our purpose is to get row echelon form. Okay, this is our purpose. Okay, so to get this purpose, you need to remember some rules. Okay, we say elementary operation. Okay, elementary operation. Yeah, we need to apply elementary operation. Okay, operation. Look, we have the first rule. We can interchange two equations. Interchange two equations. For example, we have the equation here. Here. Okay, maybe I just write randomly some equation, you know. For example, we have 2x minus y plus 3z e 4. And then we have 3x plus 5 y minus 9z is minus 6. Then minus 1x minus maybe it's minus 7x plus 1y, and then plus 1z e something like that. Okay, yeah. So we have for 2 and 3, we have 3 equations. Okay, so we can interchange. So 2 become 1 and 1 become 2. We say interchange 2 equations. Okay, we multiply one equation by a non-zero constant. Maybe I times 1 over 2 with the first equation. So I can get what? X minus 1 over 2y plus 3 over 2z e 2, right? I times 1 over 2. I times 1 over 2 with the first equation. Okay, so you get x. This one is 1 over 2 minus 1 over 2, 3 over 2, 4 over 2 is 2. Or I can add I can add a multiple of an equation to another equation. Okay, so if I apply these rules, I can get row echelon form. Okay, after some operation, I can get row echelon form. So this is the general idea. Yeah, the general idea. If you wanted to get the row echelon form, you need to apply elementary operation. And then here we have three rules. Okay, so now go details. Now we consider the first rule. Okay, we interchange. We interchange. Okay, so now we have three equation here, right? Three equation. Okay, so maybe okay. Let me see. Okay, okay, I know. So interchange, interchange. So interchange does mean we make the interchange any two rows or two columns. So here we have the linear equation. Okay, how many rows we have? The first equation we have row one. The second equation we have row two and blah blah blah. So we have Rm. That means the m order equation, right? Every linear system we have m equation and n variable. Okay, so I say R1, R2, Rm. So we can interchange any two rows. Okay, interchange. So we interchange R1 become R2 and R2 become R1. This is the first one. The second rule, multiply by a non-zero constant, or we can say multiply a row or the column. Okay, we discuss column later, right? Multiply a row by a non-zero number. Okay, I just pick up a row I. Okay, row I. So I times k with row I, and then replace into row I. Okay, or I time case with column I and replace into column I. Remember, when you multiply k with ri, you need to replace into I. And then rule 3, we add a multiple of one row or column to another. Look, we first of all we have the multiplication of k and ri. Okay, we have k times ri. That's mean a multiple of one row, right? And then add to rj, the row j, and then you should replace into rj. Okay, replace into rj. So if you say that we have k times ri plus rj and relate into ri, you are wrong. You are wrong. Remember, you replace row j by k times row I plus row j. Okay, remember, k times row I plus row j and replace into row j, not row I. Okay, remember that. Okay, yeah. Now you have 3 minutes. Try to clearly understand three rules, and if you have any question, ask me. Okay? You need to make sure you understand these three rules. Okay, we hope we have some questions. Okay, the questions. No questions. Okay, so that means Can you explain the third type again, please? Yes, of course. Okay, yes, of course. Okay, now I make the examples. I make an example and then you can understand. Okay, so now I copy it. Okay, and put here. Okay, yes, what's here? Okay, good, good. Okay, so now we should have for example here. Okay, for example, I copy it. Okay, then I put here. Pass here. Okay, good. Yeah. Okay. Now we have the linear system, right? We have the linear system. We have three equation and three variable. Okay, three equation and three variables x, y, z. So this one is row one, right? This one is row two. This one is row three. Okay. Yeah. So when I apply type one, type one, okay, we interchange. So now I rewrite the linear system like I interchange R1 and R2. Okay, so now the first equation will becomes minus x plus 3y is minus 4. And we interchange, right? So R1 become R2, you get x minus 2y plus 3z is 9. And we have 2x minus 5y plus 5z is 17. Okay, this is type 1. Do you understand? I hope so. You understand? Okay, so now we have type 2. Okay, type 2. For example, I would like to time 2 with R1, right? And replace into R1. You need to follow this. Yeah, we need to follow the rule. You get what? You can you time 2 here, so you get the 2x, right? Minus 4y plus 6x equal to 18, right? 18. And then I just copy the second row here, minus x plus the 3y is minus 4 and 2x minus 5y plus 5z is 17. Okay? Type 1, type 2. Now, type 3. Nope. Type 3. For example, I time 2 with R1 and then I plus what? Plus R2. So I need to replace into what? Into R2. Okay? So, example. Okay, so here, here, we don't care about I3, so I write here I3, right? We don't care about I3. Okay, so for I3, you get 2x minus 5y plus 5z is 17. This is I3. I3, we don't care now. 2 times R1, so 2 times R1, so you get what? So 2 times R1, so you can get what? You can get 2 here, right? 2x minus 4 for what? For y plus 6x equal to 18. Do you agree with me? Because we times 2 with R1, you get 2x minus 4y plus 6x equal to 18. And then you plus R2. After you plus R2, you need to replace into R2, not R1. So you get what? 2x. Okay, this is R1, okay? 2R1 plus R2, you get 2x minus x. You get x. 4y plus 3y minus y. 6x e 18 minus 4, you get 14. Okay, and then you just copy R1 here. R1 you get what? Keep R1, right? X minus 2y plus 3x e 9. Okay, so I explain to you, right? We have 2R1 plus R2 replace into R2. Okay, and you replace into R2 here. This is R2. So if you have 2R1 plus R2 and then relate into R1, it's wrong. It's wrong. Look, because we have, K times Ri plus Rj should relate into Rj. Okay, I hope you understand. I hope you understand. You get it? Okay, good. Thank you. So, okay. Now we have some examples before we take a break. Maybe just 2 examples. Okay. Now, here we have 2 equations. This is row 1, this is row 2. Okay, and remember that we would like to get one row echelon form, right? We would like to get row echelon form. That means the stair step. Okay, so that means we should find some way to delete this one. I would like to delete 2x. Okay, so if I delete 2x, I will get row echelon form. I will get stair step. Okay, now how do you think if I add, if I multiply minus 2 with R1 and then plus R2 replace into R2? Okay, yeah, I would like to delete this one. Okay, so if I apply the third rule, right? I add a multiple of an equation, right, to another equation and then replace into R2. Remember we have K Ri plus Rj replace into Rj. Okay, here is K Ri, right? Here is Rj, and then I replace into Rj. Okay, so if I apply this one, I can delete the top, right? Because minus 2 times R1, I can get minus 2x, right? Minus 2 and this is minus 2, you get 2y and then equal to 2, right? Minus 2 times x, you get minus 2x. Minus 2 times minus y, you get 2i, and this is, okay, and this one plus this one. So this is minus 2x, this is 2x, so becomes 0. Okay, and 2y plus y, you get 3y, and 2 minus 6. Oh, sorry, this is minus 2, sorry. I am stupid, sorry. Because we times minus 2. So minus 2 plus 6, you get 4. So now this one becomes stair step or row echelon form. Do you understand? And then now, can we get y? Yes, very easy. Now y is 4 over 3. And then you can get x, right? X is move minus y to here. So you get 1 plus y. That means 1 plus 4 over 3. So you get 7 over over 3. Okay, sorry. Oh, sorry, I erased it. Okay. Anyway, yeah, we have recorded it. Okay, I hope you can see. So now we can guess XE 7 over 3 and YE 4 over 3. Okay. Yeah, we can delete this term. Okay. So I'm sorry, I because I click eraser. Okay, so sorry, so sorry. Okay, so maybe we do another example like this. Okay, like this. This is R1. This is R2. I would like to delete this one to becomes row echelon form, right? Or step. Okay, so I think about I apply the third rule. Add a multiple of an equation to another equations. So that means we have k ri plus rj replace into rj. So here I times minus 3 with r1 and then I plus r2 replace into r2. Okay, so I keep r1, right? So if I time minus 3 here, so you get minus 3x plus minus, sorry, plus, uh, okay, minus is minus 12 because we times minus 3 with our what? Minus 3x minus 3y is minus 12. So, and then you plus r2, so you delete this one, so you get 0. And this one you get minus 6. Okay, this one is inconsistent. This one is inconsistent. Why? Because 0 is not equal to minus 6. Okay, 0y, right, is minus 6. This is inconsistent. Okay, this is non-reasonable. Non-reasonable. So we conclude that this system has no solution because we have non-reasonable equation here. Okay. Yeah. So yeah, or we can say the second equation is contradictory. Yeah, contradictory. Yeah, contradictory. So the systems have no solution. Okay. And how about here? The system has only one solution, right? The system has the unique solution. The system has only one solution. Okay, I hope you understand. Any questions? If you any question, just ask me or type the questions into the message chat. Okay, continue. Another example before we stop. We take a break. Okay, so here, look, we also apply the third rules. Okay, so here, this is R1, this is R2. We would like to delete this one. So that means I times minus 4 with R1, right? And then I plus R2 replace into R2. So if you get a minus 4, you get minus 16x plus AY E minus 4. Okay, so minus 16x plus 16x, you get 0x, right? AY minus AY, you get 0y. And minus 4 you get 0. So the second equation like this. Okay, 0x plus 0y is 0. So we have many solutions, you know. We don't care about x. Okay, with any x and y belong to real number set. Okay, this equation is always satisfied. Okay, because we have 0 here, 0 here. Okay, so we conclude that the system here has many solutions. Hey, many solutions. many solution if x is what? X is 1 minus 4 plus 1, 1 over 4 plus 1 over 2. Why? Why? Because we only have one equation here, you know. So you have 4xe 1 minus plus 2y. So that means x is 1 over 4 plus 2 over 4y become to 1 over 4 plus 1 over 2y here. Yeah. Okay. So how many solution? A lot. A lot. If I assume this y is t, t is belong to real number set. So if y is t, so you can get x is what? X is 1 over 4 plus 1 over 2 t. So we have the solution x is what? X is 1 over 4 plus 1 over 2 t and y is t. Okay, many solutions. So we conclude that the linear system has many solutions. Okay, yeah. So anyway, if we get the row echelon form like this, when we apply one of three rules here, yeah, you can get a solution. Okay, and then we have some exercise for your practice. Okay, yeah, later on I will give you some example. Now we take a break. So now is 2:35, right? So we take a break and come back to 45.